This is our lecture on flux. Flux is how we measure moving from one side of a surface to another. And although we sometimes describe this in terms of fluid because, again, that gives us kind of a concrete way to look at and hopefully understand moving from one side to another, most of the time that we calculate flux, we're actually doing it in terms of electricity and electric fields and potential on both sides of a surface, again, regarding electricity. But when we talk about moving from one side to another, we need a way to actually describe, well, which side is which, and that's where orientation comes in. And so orientation is how we're going to, well, describe flux, and that means that what we're going to be dealing with in Calc 3 is what are called oriented surfaces. Now, oriented surfaces have two sides, and while that might seem kind of obvious and trivial that I even have to say that, it turns out that not every surface is actually oriented that has two sides. The most famous example, and one that's really a lot of fun if you haven't ever played with it, is a Mobius strip, where you just take a long strip of paper and you connect the ends to each other, but before you connect them, you twist one side. And you can actually do a bunch of fun stuff with a Mobius strip. And it's actually a good, well, might actually be a good way to spend some time while you're inside and kind of play around with Mobius strips. And I'm sure you can just Google it and learn more if you want to. But the important part is that we need to have orientation, which means we need to have a way to describe moving from one side to another of our surfaces. We're going to describe orientation based on our normal vectors. So again, those normal vectors, which we use to define our tangent planes, when we're talking about, well, parametric surfaces, it's the same idea. So positive orientation means our normal vectors are pointing outward, and negative orientation means our normal vectors are going to be pointing inward. To describe our normal, we're going to use one of the facts. This was way back in chapter 14 when we were talking about the gradient and how we can use the gradient to determine, well, tangent planes, which means normals. And we had this fact that we know that our gradient is going to always be orthogonal to our surface. All right, and we went through the proof where if we have any sort of vector curve on our surface, we showed that the gradient is going to be normal to every level curve on our surface. And so that gives us a very natural way to define our unit normal. And so we're going to define our unit normal in terms of that gradient. And so it'll be our gradient, but we do want to make sure it's a unit length. So just like every other vector, we have to divide by the magnitude of that vector to ensure that we have our unit length, which gives us, again, how we can really compare the flux between two different scenarios. So the unit normal, if we're given a surface parametrically, and again, this goes back to that last set of lectures about parametric surfaces, and again, we use our general variables u and v for this definition, although, again, typically we're not actually using u and v. We showed previously that the normal can be found by finding the cross product of the two tangents, and again, to make it a normal vector that's also of unit length, we just have to divide by the magnitude of that vector, or that magnitude of the cross product. And again, like I said, most of the times we're not going to be using u's and v's. Probably the most common are cylindrical coordinates, where we're going to be using some combination of r and theta and z. Of course, we'd have to make one of them a constant, right, to do this in terms of just the two variables. Or we might even do it as spherical coordinates. And so you'd look at rho and phi and theta. But again, you got to somehow recognize how to parameterize that surface in terms of just two of those variables. Our special case, which again is probably the most common, or at least going to be half of our problems, if our surface is given in that z equals a function of x and y form, well, then we can just use this formula here. Now, note, because of the way we've kind of defined our surface integrals and stuff in the past, we're now defining z in terms of actually a function g. We're going to use the function f again, so to avoid confusion, we switch to the variable g. And again, just being consistent with the book. And I know switching a variable to make it less confusing probably doesn't make a ton of sense to us, but, you know, well, we didn't write the the textbook. So, oh well. Again, the main idea though is that if we can solve our surface for z equals and get all the other x's and y's on the other side, our unit normal is going to be found this way. And again, this comes from taking the cross product of our tangent vectors, which we did all of the work in that video on parametric surfaces. We're just basically taking it again, right? We're reusing our result from earlier. And so we see that the normal, the direction is going to be given by negative the partial with respect to x in the I hat direction, negative the partial with respect to y in the j hat direction, and 1 in the k hat direction. And then, of course, to make it a unit normal, we just divide by the magnitude of that vector, which is, again, the formula on the bottom. What you want to make a note of, though, is the fact that the component function for k hat is always 1. If we can solve our surface as that z equals, then that k hat component is always 1, which again comes from taking those partials. And that's very useful because that's going to help us actually define our orientation. Because if the k component is always 1, that means that it's always pointing up, or, well, really it's pointing up-ish, because obviously you'll have the x and the y components pointing in different directions too, but we do know that that k component, right, which is the z direction, is always 1, which means there will always be an up component to our surface. And so if we determine that positive orientation should point up, or again, up-ish, we can use just our normal, using that formula from earlier. However, if we determine that positive orientation should point down, all we do is, well, use the opposite, make everything negative. But we will still calculate the normal the same way, just again, make it negative to point down. Now we're ready to actually talk about flux. So given a continuous vector field F over an oriented surface S, and we found our unit normal to be the vector n, our flux is that surface integral, or that double integral of f dot dn, and then scaled with ds, right, which is, again, d capital S, which is those tiny patches, right, those tiny pieces of our surface. So again, hopefully this makes sense kind of intuitively. I know I sent out an introduction about flux earlier, where, again, we're taking now the dot product of our vector field and the normal. And again, the normal, right, gives us that direction where we're kind of passing through our surface, right? The tangent is along our curve, the normal is orthogonal. And so, again, this is telling us basically how we're flowing through that surface. And again, we would call that the flux of our vector field across S. Now, again, this is very similar to how we defined work when we first set up our line integrals, but of course that dot product, f dot n, by the dot product theorem, we know that that's going to be the magnitude of our field times the magnitude of the normal times cosine of theta, where theta is that angle between them. Well, just like the reason we use the unit tangent when we're calculating work, we use the unit normal here because we know the magnitude of the unit normal is 1. So that dot product is simply going to be the magnitude of f times the cosine of theta, which really just gives us that component of our force in that normal direction. Now, again, going back to what we've talked about before, if we have that parametric surface given in terms of the variables u and v, our unit normal, we already talked about that, is going to be the cross product of our tangent vectors, and we normalize it by dividing by the magnitude. And from our previous video also, we showed that we scale ds, right, when we're doing surface integrals, we scale that ds with the magnitude of the cross product of our two tangent vectors times dA. So what that means is that, again, given our general formula for flux, and again, this is the conceptual idea for flux, and it actually also works fairly well as a computational formula as well, but we can actually, well, help ourselves out a little bit and do a little bit of math to make it a slightly nicer computational formula as well. And so if I just make that substitutions, and so, again, looks kind of like a mess, but I'm just replacing n with how we defined our unit normal, and I'm replacing ds with how we defined our kind of our scaling factor to switch from ds to dA, which again is going to let us go from our surface in 3 dimensions to a 2-dimensional region again, typically given by d, which allows us to actually take a double integral with only, well, two variables or two parameters. But hopefully we can see if we make that substitution, well, those magnitudes are going to cancel out, right? That's the same magnitude. So those magnitudes will cancel out. So flux is really just going to be the dot product of f with that cross product, and then dA. And again, we'd have to scale it though. But this gives us other notations for flux as well that you might see. Probably the second most popular way we describe flux is that if our surface is parameterized as a vector function, we can actually rewrite flux as just f dot ds. And again, remember, ds means we're taking the derivative of our vector function. And again, our vector function is now parameterized as a vector function. So ds, and just for the same reason we mentioned with the gradient, we know that the gradient is normal. And so we're taking the dot product with the normal and writing it as a, well, kind of a derivative. And so this is another kind of useful computational and conceptual idea of what's going on with flux that again brings us back to that whole concept that, well, the gradient, right, or our derivative is always going to be normal or orthogonal to our original surface. If again we have that special case where I can solve for z equals and then some function, of x's and y's, and again our vector function, our vector field, is given by our typical p I hat plus q j hat plus r k hat. We can combine that together with our dot product very easily and see that, well, we're going to end up with, when we calculate flux, just doing minus p times the partial of g with respect to x. And the reason that minus sign shows up is, again, if you go back, remember when we defined the normal, what we're really doing is going to be p times, and the component of our normal was negative partial g with respect to x. And then again, it's a dot product, so we would sum it. But then the next one, it was q times negative partial of g with respect to y, plus, and then r times, well, 1. And again, this gives us a very nice formula to get a scalar function that we can integrate over. And it's probably the most useful one, again, that, well, for any time that we're actually given our surface as a function of two variables, right? Where I can get that z by itself. This is the important one you really want to put a box around and make sure you're comfortable using. So to calculate flux, so we've been doing a lot of different problems here when we're talking about parameterizing surfaces. We talked about parameterizing surfaces, just coming up with a parameterization. We talked about tangent planes. We talked about surface areas. We talked about surface integrals, and now we're talking about flux. And yeah, they're all very much related to one another, and they all use the same basic skill set. But you're going to have to do, well, slightly different things depending on the type of problem. And so with flux, the first step is to just parameterize. Again, I want to rewrite my surface as z equals g of xy if I can. And that gives me my parameterization. Then I can substitute that parameterization to rewrite my vector field f in terms of just my two variables. And again, once I do that, most of the work is done. Again, a lot of this is just figuring out how I can parameterize to write the entire problem in terms of two variables. And once I have those two variables, then it's really just using that formula for flux. And so, again, once I've parameterized, which is the first step, the second step is to find our partials so that I can help define what my integrand is going to be, what I'm actually going to integrate. And then, well, I'm going to consider my projection of S into that xy plane. And again, that's how I'm going to take my region, which is in 3 dimensions, right? My surface, actually, which is in 3 dimensions, and describe it as a region that is just in 2 dimensions. It's how we convert between dimensions. It's how we convert between 3 dimensions and 2 dimensions, which is, again, kind of an incredible mathematical skill that we don't always take the time to really appreciate, that I can take a problem that is in a higher dimension and simplify it to one that is actually in a lower dimension. That makes it much easier to do. And that is actually the crux of actually Einstein's genius as well, when he discovered that we live in a 4-dimensional world, but we just can't understand that, right? We don't see that because just like an ant walking on a sheet of paper, or a human walking on the Earth who thinks that the Earth is flat, we can't detect the curvature because of, well, our position in the universe. And this is that same idea, that same concept that gets used in a lot of modern physics, where you're going to see we want to take these problems that are in higher dimensions and translate them down to lower dimensions. And it's going to be that critical skill that will probably follow you for the rest of the time you're taking physics classes. And then, well, once you do that, though, I mean, the problem is fairly straightforward. Once I can write it down to that two-dimensional region D, then everything's in my integral. And it's just doing the integration, taking that double integral and using all of our integration techniques that we have developed over, the past year or longer that we've done calculus. So we're going to follow these steps, and I'm going to do an example for you. For this example, we're asked to calculate flux. And, well, here's our formula for flux. We need to evaluate the surface integral of f dot dn. And so, it's pretty straightforward. Really, all we have to do is find f and find n, take their dot product, and put it into our integral. But the challenge is going to come from the fact that it's a surface integral, which means it's a double integral, which means I need to use only two variables or two parameters. Which means, really, step one is just to parameterize. I need to be able to take my field f and my normal vector n and write them in terms of the same two variables or parameters. And that's really going to give us basically the blueprints about how we're going to work our way through every single example that asks us to calculate flux. So we do have f given, but my parameterization is always going to be based on my surface. And in this case, my surface S is this plane, and this is going to be one of those special cases where, even though it's not written like it to begin with, I can very easily take my plane and solve it for the variable z. So that I can parameterize in this case as z equals that function g of xy. And again, shouldn't be very difficult algebra to get z by itself here. Basically subtract the 2x, subtract the y, and then, well, divide everything by 2. And if I divide everything by 2, so it's going to give me 2 minus x minus 1/2 y. And there's my parameterization. I'm good. Now my parameterization, my surface, is in terms of just the variables x and y, which means when I find the normal for the surface, it'll be in terms of just x and y. And so the next step to parameterize is to try to parameterize my function for the vector field f. Well, here's where we want to be careful, and again, I kind of picked this example on purpose. When we parameterize, we have to go through component by component. Right? It's not kind of like the other ones where it's, x for I hat, y for j hat, and z for k hat. In this case, we're actually given a vector field, and we're going to have to make our substitutions into that given vector field. So in this case, my vector field, right, my I hat component is z I hat. So in this case, I need to substitute, well, what's z? What's this whole thing that I found here? So z is going to be really 2 minus x minus 1/2 y. And that's my I hat component. So I hat minus yj hat. Well, I don't need to parameterize that. That's still in terms of my two variables that I'm going to use, x's and y's. So that's just going to stay yj hat. And then finally, plus xk hat. And again, there's no issues there. And so there's my parameterization. And again, this step is basically going to guide how the rest of the problem goes. I have my vector function in terms of my two parameters, x and y. I have my function in terms of the, well, I guess my surface actually in terms of the function g, which is in terms of just x and y. And we're good. Now that everything is parameterized, now we can actually go ahead and do a little bit of calculus. Now that I have my parameterization for g, I need to find those partials, g partial x and g partial y. And again, you're going to notice the same patterns happening over and over again in these problems of parameterizing and finding partials. Just make sure, again, you're doing the homework enough and spending enough time with it that you are understanding whether you're doing a surface integral problem or a flux problem, because there are going to be some subtle differences. But again, a lot of it will remain the same, which should hopefully make it at least be kind of easy, and then you don't have as much to memorize in terms of like new things to do. Now, the partials in this case should be pretty straightforward. Hopefully you kind of did it in your head already. But if not, we'll go through the partial with respect to x. Now, 2, that's a constant, goes away. What's the partial of negative x with respect to x? Well, just negative 1. And y, that's a constant, so that's going to go away. And then the partial with respect to y. Well, again, constant goes away, so the only thing that's going to be left is negative 1/2. Now remember, these partials, they're going to be what I use to help define my normal vector n. Alright? They're going to be used to help define my normal vector n, or, well, that other notation we were using, how I would represent ds, where my s is given by a vector function now. But before we can actually evaluate this integral and plug everything in, let's find out what our bounds of integration are going to be. To find out what the bounds of my integral are going to be to calculate flux, well, I need to figure out how I'm going to define my region D. And in this case, we already know that our parameterization is going to be in terms of x's and y's, which means my region D has to take place in the xy plane. And again, this is one of those places where being able to write your surface in terms of the z equals becomes really nice, because it's just always going to be that projection into the xy plane, which is always going to just be the projection when, well, z equals 0. So, from the problem we know that, again, we have the equation of the plane. It's in our first octant. Remember, the first octant is kind of similar to the first quadrant, and it will be the first quadrant when we actually, well, put it into just 2 dimensions in our region D. And so again, if I take this plane and set z equal to 0, well, it just gets rid of that portion. And you could use the parameterized form if you wanted to. It'll be the same thing. But this is what I end up with, which equals 4. So I have 2x plus y equals 4. 2x plus y equals 4. And although you could do this a bunch of different ways, I think the easiest way is to just rewrite this as y equals minus 2x plus 4, and we know what that line's going to look like. Here's my line, y equals minus 2x plus 4. And we're going to have to set this up, so we might as well set this up as a type 1 double integral, which means we bound x with our constants. So clearly x is going from 0 to, and again, do a little bit of algebra if you need to, but right, solve, what is it going to be? 0, 2. So x is bounded between 0 and 2, and then y is going to be bounded, well again, my region D is this triangle, right, that's bounded in the quadrant. So the lower limit is 0, and my upper limit is going to be, well, my function, minus 2x plus 4. And now we're actually just about ready to put this all together. Alright, now we're ready to plug everything into our integral. So we are going to use, again, that special case where we can actually evaluate flux. We actually do it the dot product here, and so again, P minus G partial X, Q minus partial Y, and R times 1. And again, this goes back to how we define that normal back in the parametric surfaces, right? And yeah, so it's just a matter of, at this point, plugging everything in. So, okay, integrating, we know we're integrated from 0 to 2 for x. Y is being integrated from 0 to minus 2x plus 4. Which means, again, over here at the end, we'll do with respect to y first, and then the outside one will be with respect to x. And, yeah, now we just plug everything in. So, minus p. Now, again, I rewrote my vector function, right, in that parameterized form. So, remember, p is going to be this entire function here. So, minus the quantity 2 minus x minus 1/2 y times the partial with respect to x. But we said that partial with respect to x was just -1, so not too bad there. And then we'll move over. So minus, and then q. Well, q was minus y, so minus y times the partial with respect to y, which was -1/2. And then finally plus r. And r in this case was just x. And then, like I said, we're doing it with respect to y first, and then with respect to x. So before we actually try to integrate, let's actually clean up, well, my integrand here, if I can, just a bit. So the minus and this minus 1, those are going to cancel out. So I just have 2 minus x minus 1 half y. Over here, I have minus, minus, minus. So basically a triple minus. I still get a minus 1 half y. So let's see, there's that. And then this plus x. So, well, it looks like, all right, minus x plus x. Those will cancel out. So now I don't even have any x's left. So I have the 2. That's kind of stuck there. And then minus 1 half y. Minus 1 half y is just minus y. So my integrand actually simplifies quite nicely as just 2 minus y. And then now my first integral is going to be to integrate with respect to y. Again, we'll do that one first. And my bounds. But let me get a clean board to work this one out. Well, here's the first part of our iterated integral. And this integration is actually going to be pretty easy. Because what's the antiderivative of 2 with respect to y? 2y. And the antiderivative of y with respect to y, so minus 1 half y squared. And we're evaluating from 0 to negative 2x plus 4. All right, well, let's just plug in our bounds then. So, plugging in my upper bound. So I'm going to get 2 times the quantity, negative 2x plus 4, minus 1 half, and then that quantity, minus 2x plus 4 squared. And plugging in my upper bounds, minus, well, 0, right? If I plug in a 0, that's got to be 0 everywhere. So now it's just a matter of, again, kind of cleaning this up before we do our second part of the iterated integral, which is actually to integrate with respect to x. Now, this shouldn't be too bad. So the first one, distribute. So that gives me minus 4x plus 8. And over here, I expand this. Minus 1 half. And I'm going to expand this first. Again, just kind of using the binomial theorem. So that's going to give me 4x squared minus 16x plus 16. All right, and if I distribute through that 1 half, that becomes a 2, an 8, and an 8. So let's see, can I clean this up any further? I believe I can. So I have minus, let's see, so minus 2x squared, do it in standard form, minus 4x and minus 8x would be minus 12x, and then plus 8 plus 16, so plus 24. Alright, and I can actually factor a 2 out if I wanted to. I probably won't. But now we're ready to do that second iterated integral. So, give me a second to go back to the top. Alright, we're on our last step. This is it. Just have to integrate this with respect to x, plug in my bounds, and this problem will be done. So, let's integrate. So what's the antiderivative of minus 2x squared? Well, it'll be minus 2/3 x cubed minus, well, the antiderivative of 12x is 6x squared, and the antiderivative of 24 is 24x. We're evaluating from 0 to 2. All right, so I just got to plug in my limits. So let's plug in 2. All right, so negative 2/3 times 2 cubed minus 6 times 2 squared plus 24 times 2 minus, well, and then the other part 0. So let's see here. Clean this up. So 2 cubed is 8. So negative 2/3 times 8. So negative 16/3 minus, okay, 6 times 2 squared. Well, 2 squared is 4. 4 times 6, so minus 24. And then plus 24 times 2 is 48. All right. we're almost there. So let's see. So 48 minus 24 is really just plus 24. Want to do common denominator stuff here. 24 is really 72 thirds. So 72 thirds minus 16, d 6 thirds, 56 thirds, and that is my answer, 56 thirds. There we go. This is basically how we do our flux integrals. Again, these surface integrals and these flux integrals can get a little tedious at times and do require a lot of steps, and there's lots of places to make mistakes, so you really do have to be diligent. You really need to keep track of your work, label everything as well as you possibly can. My suggestion is to write big so you don't lose any minus signs anywhere, and just, again, put care into your work. There is no way to produce quality work without putting in care, and please, please put in a little bit of care so that this goes well.